I'll speak a bit. So I'll give a short introduction to these SMT solvers and how we can leverage them today to verify some parts of the compilers. So, but first of all, so why should we care about verifying these optimizations? And the reason is basically twofold. So first, we can catch the bugs even before they exist. Okay, so if you are just thinking in your new algorithm, if you are designing your new like InstCombine pattern, whatever, even before you write the code, you can verify that these are in fact correct. Okay, and I think we all know that debugging these like wrong code emission bugs is really hard, right? And it takes a lot of time. So my point here is that it pays off. So in the long term. So although you will spend some time doing conditional verification, in the long run, you'll save a lot of time in this debugging. Okay, and I'll only talk about technology that's developed today, not any stuff that will be available in 10 years. Okay. But let me show you a famous quote from Knut, a very old quote. And I'm not trying to, so I'm not saying that we should get rid of all testing, whatever. So I'm saying that we should do verification in addition to testing, okay? And I will elaborate a bit more later on this. Okay, so this is the outline of the talk. So I'll start with a short introduction to SAT and SMT solvers. And then the rest of the talk will be with examples. So I'll show a bunch of examples on how to prove like InstCombine, for example, some assembly code to check whether it matches to the IR code, and some data structures, and I'll use the constant range as an example. Okay, SAT solver. So who has used a SAT solver before here? Okay, 3 people, 4 people. Okay. Well, a SAT solver is a pretty simple tool. So it takes a Boolean formula as input. So you can say, well, A or B or C and not B or C. And what the SAT solver will try to find is a set of values for these variables that makes the formula true. Okay, it's very simple. So the SAT solver can return either SAT if you can find such an assignment, or it can return unsat if the formula is always false, regardless of what values you put in A, B, or C. Okay, and if the formula is satisfiable, we also get the model, and the model is an assignment to these variables. Okay, so in this example, if you replace A with true, B with false, and C with false, you get true. Okay, and there might be multiple models for some formula, so the solver is free to choose any of them. Okay, so this is what a SAT solver does. It's pretty simple. You can think that the naive SAT solver will just try all possible combinations, and you'll get some exponential algorithm. But today's SAT solver are way better than this exponential. Okay. Okay, so SMT solver is a generalization of a SAT solver, and the difference is that the variables are not only Boolean, so they can take different different domains, including, for example, bit vectors, which is what we are going to use today. Okay, and that's it. So there are many available SMT solvers out there. I'm not particularly endorsing any of these. These are the ones that I've used in the past, so they actually work. I like Z3 because they have this web service online, so you can do the proofs in your browser, so you don't need to install anything. Okay. With the disclaimer that I've worked in the Z3 team in the past, so of course I have to say that it's the best one. And also the warning is you should read the license of these tools before using them, because not all tools have a suitable license for your usage, probably. So anyway. The bit vector theory of SMT solvers, which is what we care about, so it basically supports all operations that you see in the LLVM IR, okay, so all the standard operations. And with addition to 2 operations, which is this concat that takes 2 bit vectors and concatenates in 1 bit vector, and the extract, which takes a bit vector and extracts a set of contiguous bits of some bit vector, okay? And the other important thing is that a variable as a fixed bit width. So once you declare variable a with 32 bits, then it is 32 bits forever. Okay. And also, you have to declare the variables with a constant bit width. So you cannot say I have a variable a of x bits. Okay, so it has to be a variable a of 32 bits. Right. We'll see later why this is important. Anyway, enough of talk. So let's look to some example. So let's prove that these two expressions are in fact equivalent. So who thinks that these expressions are actually equivalent? So no one? So who thinks that they are not equivalent? Okay, so everyone is shy? Or, well, if you're not experienced with this InstCombine style of patterns, it might not be obvious when you look at it, right? But this is probably InstCombine 101 transformation. And does anyone know actually what this expression is trying to compute? Power of 2? Well, not almost. Almost. OK, but now shut down your LLVM part of the brain, and let's think as a SMT solver. And what do you need to prove? So what do we need to prove in order to be sure that these expressions are equivalent? Okay. So there are two ways of looking at this. So we can think, OK, so for all possible values of x, these expressions always return the same value. Okay. This is one way of looking at it. Or we can say, well, there is no I cannot find a value for x such that these expressions are different. Okay. Well, the second one is a bit more complex, but we know from logic that that these two statements are actually equivalent. Okay. And the second thing is that SMT solvers prefer the second version because they don't like these for all x something somethings. Okay, so they prefer these. There is no value or there exists some value. Okay, so we have to encode the problem in the second form. Okay, so let's do it. So in the bottom right, I include the URL to the Z3 web service. So you can see the proof there, and you can play with it. So basically, the website has a play button. You can play, and it proves for you. So first of all, we declare a variable x of 32 bits. So the syntax is Lisp-like. So we'll see a lot of parentheses in this talk. Actually, we are declaring a function. So everything in SMT is a function. So we say we have a function from null to a bit vector of 32 bits. And then we say, well, I want to find, so I have two expressions now that are not equal. Okay, so let's encode the first expression, again, with a lot of parentheses. And the functions are prefixed with the BV, which is short for bit vector. So you can say, well, I have this x ended with x minus 1 equal to 0, right? Then we encode the second expression. And finally, you say, well, is it satisfiable or not? Okay, so what this example is saying, again, is, well, is there any value for x which makes these two expressions return a different value? So that's what we are asking from the SMT solver. And if you run this, after a few milliseconds, we get unsat. This means that there is no possible value for x such that these expressions are different, which means that they're always equal. So we have just proved that these two expressions are equivalent. So from now on, you can be sure that you can use either of them because they are equivalent. Okay? So we didn't need to think about it. We just give to the tool and play and press a button. OK, but then Dimitri said, well, this is a power of 2. But are we sure that it is testing for power of 2? Well, I'm not. So let's ask the solver. So I define x with 4 bits because I don't want to enumerate all the power of 2 up to 32 bits. Okay. And then let's say, well, is this equivalent to being equal to 1, 2, 4, or 8, which are all power of 2 of 4 bits? And then I ask, well, is it satisfiable or not? And it says it is. This means that the expression is not computing the power of 2. So Dimitri was almost correct. But now the SMT solver can do a bit more, which is it can give me a value for x such that these two expressions are different. So we ask for the model. And this says, well, if x is equal to 0, then these two expressions are different. If you plug 0 in the first expression, we get like 0 and something equal to 0, which is true. And in the second expression, we get false. Okay? So the first expression is almost the power of 2, except for the case where x is equal to 0. Okay. So I give for your homework to fix the first expression to put and not x is equal to 0. And if you put that, then you can prove that the expressions are equivalent. Okay. And then you have just proved that the expression, at least for 4 bits, returns true if x is a power of 2. Okay. Okay. So now that you are all experts in SMT, let's go for more complex example. So let's look at InstCombine. Okay, so InstCombine doesn't really need any introduction here. The point is that it's a really cool target for SMT solvers because InstCombine is just converting this little sequence of instructions into some other sequence of instructions. Okay, so there are no loops or nothing. It's just very simple straight line code. Okay, so let's look at this example. So a few months ago, someone sent an email to the mailing list saying, well, I'd like to do this transformation, okay? And the first time I look at it, it was not really clear to me whether it was correct or not, okay? Does anyone have an opinion? So I can give you a hint. So this was committed to LLVM. And then it was reverted. So, so some people thought it was correct, so it got committed. Then it broke Clang self-host, and then it was reverted. But let's actually prove that it is not correct, or if it is correct. Okay. Okay. Again, so I show here the full code because you're all experts now, so you know how to read this. And let's ask the solver, so check sat. And it says, well, it's satisfiable, so they are not equivalent. So this InstCombine pattern apparently is not correct. But now we can ask for the model. And it says, well, if A is 0, and if B is that huge number, 20,007, then the expressions are not equivalent. But B, if you see like here, it's a value where we do the left shift. But if you remember from C, overflow in left shift, it's undefined. So we don't care whether these expressions are equivalent for this case. Okay. So we can ask, so the question that we should ask is, are these expressions equivalent for the cases where we have defined behavior, right? So let's do it. Again, we define the variables. Now we say, well, B must be unsigned lower or equal to 31. Okay? And this condition guarantees that the left shift won't overflow, okay? Because it's between 0 and 31. And now we copy paste the rest of the script, and the SMT solver says unsat. Okay? So in fact, this InstCombine transformation is correct if we assume that the left shift overflow is undefined behavior. Okay? I think this is really cool because the first time you look at this transformation, at least I was not sure whether it was correct or not. And now we are sure that it is because we are leveraging certain undefined behavior. So if you look to the InstCombine code, well, it's, I don't know how many thousands of lines of code, and you are not sure where we are leveraging undefined behavior, where we are not. So if you want to change the semantic of the IR for your language, you are not sure where to start changing, right? But here we are now sure what undefined behavior we are leveraging. Okay. So the whole story was, so this patch was committed and it was reverted because apparently Clang was executing some undefined behavior. And I think the patch never came back again. So I don't know if the bug was fixed in Clang in the meantime, but I think we are not doing this transformation at this point. Okay. Okay, so let's look at some assembly code to see that we can also do something different. Okay, another real story. So I submitted this bug report about the built-in overflow intrinsics. Okay, so I wanted to do x times y plus z and get 0 if any of these operations overflows, or otherwise return the result of the operation. Okay, and LLVM was giving me 17 instructions of pure madness, which was like a horrible sequence of code that was crazy, basically. Okay, so this code compiles to this LLVM IR. Okay, so these built-ins return two values. One is the result of the operation, and the second value is a Boolean indicating whether the operation overflowed or not. Okay, and the LLVM was compiling these to this bunch of garbage. Okay, which does like push flags, pop flags, and you have there move EAX, VCX, move ECX back to EAX. So this is completely insane. Okay, 17 instructions. And then I said, well, maybe we can compile to just 8 instructions. Okay. So it's, well, it doesn't matter what the code is. But then Michael analyzed the bug report and said, well, your code is not really correct, because instead of this add carry EDX, EDX, we should have a add carry 0 EDX, because your operation may overflow, and then this is not really equivalent. And then I was really puzzled, because I thought that my code was actually good. And he said, no, it's not. And then I went ahead and asked the power of SMT to prove which version was actually good, or if both were wrong, or if both were good. Because this version, so the encoding of this add carry takes more space than the add carry EDX, EDX. Okay? So if the other was correct, it was better to use the other, right? So now we can compare this assembly code to the LLVM IR to see if they have the same semantic. Okay. Okay. So the first instruction is this mul. So this is multiplying x by y. And the semantics of x86 multiplication is that we 0x10 to 64 bits. Okay. And we do the multiplication in 64 bits. And then EAX takes the less significant bits, so we do the extract. So the extract counts from right to left, so it's 0 to 31. And the EDX takes the most significant bits, okay? And that's the encoding for the multiplication. And then we do the addition, so we add the previous result with Z. Okay? It's simple as this. And we also update the carry flag, because this instruction also updates the carry flag. And we can do this by doing the addition in 33 bits and taking the sign bit, right? Now we have the add carry. So what the add carry does, so it adds EDX, EDX plus the carry flag. But we need to 0x10 to 32 bits, because the type checker requires all operands to have the same bit width. Okay. But add carry also updates the 0 flag. So the 0 flag will be 1 if the result is 0. Okay. And finally, we are left with this set of jumps. So basically, what it does is, if 0 flag is 0, we jump to the shore, to the XOR, and where we 0 out EAX. Otherwise, we just return whatever is in EAX. And so we can define something like this. So we have this new operator, which is if then else. So if 0 flag, we return whatever is in EAX. Otherwise, we return 0. Okay. So now we have the result of what the assembly code is computing, right? Now let's see what the IR is computing. So it says, well, if I have overflow, but by the way, these let expressions are what you would expect from these functional languages. So this is like a local variable. So I have overflow if I do the multiplication in 64 bits and the result doesn't fit in 32 bits. Or if I do the addition in 33 bits. Well, actually here I'm doing in 36 because so that I can use the hexadecimal notation, right? I'm lazy. So if any of the operation overflow, then the whole thing overflows. And then if overflows, I return 0, otherwise I return the result of the operation, okay? So now we have two expressions. One says whatever the assembly code is computing and what the IR is computing, right? And now we can say, well, can you find me X, Y, and Z such that they are computing different values, okay? And it says, well, yes. So they are not equivalent, okay? So it means that Michael was right. So the proposed assembly, so that those 8 instructions were actually wrong. And then it returns a model with these weird values. And I challenge you, if we didn't prove this way, how you could have found this in the real life? Like these values are really weird, so how could you trigger this bug, right? Oh, Michael is actually there. Yes, so that's correct. So Michael found it, so we don't need SMT Solvers, so let's go home. And yeah, so and Michael, of course, has been working with this bit stuff for a long time, but so it's easier for him to find these kind of bugs. But for me, which I only work in these things once in a while, so it's harder to catch these bugs, right? So actually, the model here, I'm not showing the whole thing, but it also shows the values for EAX and DDX and the carry flags and whatever, right? So I leave you for your homework, which is to prove that Michael's version is actually correct, okay? So instead of doing the @carry EDX EDX carry flag, it's just @carry 0 EDX carry flag. And his version is correct, okay? So Michael was correct from the beginning, but I thought this gives a great example of what we can do. Okay, and yeah, that's it. So let's see a last example. So how we can use this to prove that certain data structure of LLVM are also good, okay? This is a bit trickier example. Okay, so constant range is a really cute data structure of LLVM, which represents as ranges of integers, okay? But with overflow semantics. So we can have this interval from 5 to 2, which means that we go from 5 to max integer, and then with union with 0 from 2, or from, okay? And it is used to perform optimizations using range analysis information. And then this data structure supports many LLVM IR operations. So you can do additions and multiplications between these ranges. And from this simple description, you can maybe naively think, as I thought in the past, that it's not that hard to implement this data structure, right? And the answer is wrong. So this is actually pretty hard to implement. And there have been a lot of bugs in the past in this file, both of correctness and optimality. So this makes a really nice target to prove the correctness of this thing, okay? So let's take a look to the simplest operation that constant range has, which is this signExtend, okay? It's just 8 lines of C++ code, so what can go wrong in 8 lines of code, right? I don't know, so I decided to go ahead and prove that these 8 lines of code are doing what we expect. Or maybe not, let's see. Okay, so first we need to define some definitions. So this defined sort is like a type def. Okay, so we are going to define, well, let's do operations on integers of 32 bits, and let's define an interval as a concatenation of 2 integers, okay? So an interval will be a bit vector of 64 bits. And the result, so here I'll be proving a signExtend from 32 to 36 bits, okay? So the resulting interval will be 72 bits. Okay, and then let's define some functions. So this will extract the lower part of the interval and the upper limit of the interval, okay? Then we can define all the auxiliary functions like isFullSet. This is just copy-paste from the C++ code, okay? So just put the parentheses before the functions, and this is equal to whatever it's in C++, okay? And of course, there is also, we use empty set, use sign wrap set, whatever, but I'm not showing here. Okay, so let's convert signExtend to SMT. It's pretty simple. So we define this function, signExtend, that takes an interval of 64 bits and returns an interval of 72 bits. Then we do if then else. So if I get an empty set, I return an empty set, so first line. Then if I get a full set or a signed wrapped set, I return that weird thing. So here I've just constant fold whatever API int is doing. So I didn't bother implementing API int, but those are constants. Otherwise, we return the signExtends of the limits, okay? And this is all what these 8 lines of C++ are doing, okay? So I don't know if you agree, but it seems to me that it's a pretty standard transformation from the C++ code to this SMT, okay? Okay, and now we can ask, well, is it correct or not? And now, again, we need to think what it means for this operation to be correct. And the correctness criteria is that if we pick one element of some interval and we do a signExtend, then this signExtended value should be contained in the signExtend version of the interval, okay? And that's what we need to ask. So we define an integer and an interval. Then we say, well, I have some integer which is contained in some interval. And now let's try to find such an integer which is not which the signExtend is not contained in the signExtend of the interval. Okay, this sounds a bit tricky at the first time you do this, but then it becomes pretty straightforward. Okay, and now we can say, well, is this correct or not? And it says, well, unsat. So it means that signExtend is correct. So okay, so from now on you can rely on constant when signExtend, which is doing the right thing. Okay. Okay, it's all pretty cool. It's correct, but if we implement signExtend as always returning a full set, it is always correct, right? Because it's an approximation of the result, so it's always correct. But then it's not very helpful for performing optimizations, right? Because we want to know the tightest possible interval for the operation. So now let's do something different and try to prove that it's actually returning the best possible solution, okay? So we are going to try to prove that it is optimal. Okay. This is a bit trickier. So let's see. So let's define 2 intervals. R is the result interval, which is some other result interval than the one that we are computing, okay? Then we say, well, find me some result interval which is smaller than what we are getting by applying signExtend, okay? But now we have to define that is also a correct solution, that R is also a correct solution. So now we need to go to the power of the for all quantifier and say, well, if for all possible numbers that are in this interval n, the signExtended of this value must be in this result interval R, okay? So this formula is a bit trickier than what we saw before. But to check for optimality, then we need to go for this for all quantifier. So I don't really expect you to understand the whole thing today, but you have the URL there, and then you can play with this in your browser later. Okay. Okay. Now so in Z3, when you are using these quantified bit vectors, you should use this line. Okay. Because, okay, so this line means you should use a different algorithm, okay? So this is just a Z3 technicality. For other solvers, just use checksat as usual, okay? And Z3 says, well, it's not optimal, okay? So Z3 found a model where signExtend is not returning the best possible solution. But this solution is a bit tricky to read, right? Because we define the interval as a concatenation of integers, whatever. So SMT has some functionalities to help us. So we have this eval, which prints evaluation of expressions in the model. So we can ask, well, what are the limits of these intervals and the limits of the results of the signExtend? And it can give us some values, okay? I'm not going to debug this video online, but the problem is that thing in bold, okay? So which is the int min. So it is not optimal when the upper limit is int min. So last week, I don't know if you noticed on the mailing list, but I did this commit to signExtend, which basically checks for this case. And now you have the URL, and you can check that, in fact, now signExtend is optimal. So not only we are sure that signExtend is correct, now we know that it's always returning the best possible value, okay? So I have two URLs there because one is 32 bits and the other is only 8. Because like with 32 bits, it takes a long time to verify. So it's like with 8 bits is like a few milliseconds, with 12 bits is 6 minutes, and with 32 bits, I didn't bother waiting, okay? So this, I proved that it is optimal for 12 bits, okay? And now we can pray that it's also optimal for 32 bits, okay? Anyway, I think it's better than just not knowing what's happening there. Okay, so let me just share some of my thoughts for the future. So of course, we'd love to have automatic translation from C++ to SMT, right? And it's not actually very difficult because you saw that there is like a mechanical translation from the C++ to SMT. So we could have some front end that knows about LLVM code and how it is structured and just transform automatically. The second thing, so I didn't talk about, but the functions in SMT are not recursive, so you cannot do recursion on the functions. But some solvers, including Z3, already have support for recursive functions in the form of these horn clauses. So I expect to be able to verify a lot more things in like a few months, okay, with these horn clauses. The third point is floating point, okay? So SMT solvers are also coming with a floating point these days. And I think this is a really cool opportunity for example, OpenCL. Because OpenCL, the standard, defines the maximum error that the compiler can introduce when optimizing some expression. And with the SMT solver, we can actually prove that we are respecting that bound for error. Because if InstCombine patterns are difficult, like InstCombine patterns for floating point are very hard, right? So it's really hard to reason about floating point transformations, at least for me. Actually, then, so I would really love to be able to verify a few more complex stuff. So I think scalar evolution, so constant range is already hard to implement, right? Scalar evolution is really hard, okay? So it would be really nice if you could just verify that scalar evolution is okay, because it has also been a source of bugs like in the past, because it's a really hard thing. And finally, termination checking. So we have seen a lot of bugs like in InstCombine and selection DAG related stuff that do canonicalization of the IR. And it's really easy to implement a pattern there that it go back and forth, and then we have some infinite loop. But today in verification community, we already have some techniques to check for termination. So I think a good next step is to prove that InstCombine will never go into an infinite loop. Yeah. OK, so just to summarize, I tried to convince you that there is already some potential like verification technology that we can use today to avoid some bugs. And I think it's ideal for these kinds of what if I do this change questions, okay? Because I want to optimize this little thing, so what happens? So will the code be equivalent to the one that was before or not? I also leave here some links. So SMT also supports arrays, so I didn't go there, but you can also use it. And there's Stack Overflow, so there's a bunch of people there always answering questions about SMT, including myself. But you can also email me directly if you want. And last but not least, I would like to thank CodePlay for sponsoring my trip here, which otherwise wouldn't have been possible. And yeah, that's it. Thank you.
There we have 4 minutes for questions. Oh, if anyone has a question, just come up to the microphone.
Question. I can just ask them over here. I think my voice carries enough. Is that okay? Or you need to
For the recording.
They're recording them.
Yeah,
Yeah, right, yeah.
My question is about the support for recursion in the solver in Z3. That's something that we wanted to use in a project ourselves. In fact, there'll be a talk today about our work. And we didn't do it because we couldn't find one that had reasonable support for recursion. You said they've been adding it. How well does it work, and what can you use it for?
Yeah, so the recursion is coming along. So Z3 already has like 3 solvers for recursive horn clauses. So horn clauses are pretty expensive. So you can map like functions of C that have unlimited stack usage to horn clauses. And we have a front end that goes from C to horn clauses. And the Z3 solver already works pretty well for certain theories. So it means that it can do integers, right. It can do booleans. For bit vectors, it's not awesome, but I can show you how to use it. And if you look to the software verification competition that is running already for 3 years, most tools are already using this horn clause solver. Okay. There are already like Z3, our own model checker also uses horn clauses. And so I think it's already very usable, and yeah, okay. You can use it. I can show you offline how to use it.
I can talk to you more about that.
Is there any tool you could like write your proof and extract the like C++ code from it, so you could like write parts of InstCombine in this file, which like as part of compilation it proves it's correct, or at least as part of like
so
make check it proves it's correct.
That's actually part of my evil plan. So that's something that I've also been talking with Jacob for Selection DAG. So it would be really cool if we could specify this thing in some DSL, right? And then we extract the proof and the C++ code all from the same place. It should work for InstCombine, for DAG legalizer, DAG combiner, whatever. So I think that's like long term. I think that's the solution for LLVM. Because right now, like InstCombine is just a huge chunk of code that it's insane. It's very big. Okay.
Okay. Well, let's thank Nuno again.
Thank you.